Okay, let us discuss the problem number 2.48. So this is an ideal gas whose adiabatic exponent is gamma. So it's an ideal gas. And Cp by Cv is given to you, that is gamma. Expanded according to following law. So this ideal gas follow a law, that is P is equals to alpha times V. So P is given by alpha times V, where alpha is a constant. So alpha is basically a constant. The initial volume is V naught. So initial volume, let us call V1 is equals to V naught. And as a result of expansion, the volume increases eta times. So let us say final volume is V2, that is eta times V naught. Increases V eta times. So the final volume is eta times V naught. Find the increment in internal energy. First part A says, find out change in internal energy, that is dU. So what is the change in internal energy? If you remember, we have formula du is equals to ncv dt. So I have to find T2 minus T1. dt is ncv, number of mole, Cv T2 minus T1. So I have to find T2 minus T1. And let me see number of mole is given or not. So ideal gas whose adiabatic exponent is gamma, N is also not given. So I think it will be eliminated. So if I apply ideal gas law, PV is equals to nRT, and equation says P is equals to alpha V. So if I write alpha V into V, this is equals to nRT. So from here I can write alpha V square is equals to nRT. Now initial volume is V naught, so T1 will be, so let us plug T1, initial volume is V naught, so T1 will be alpha V naught square divided by N into R. So this is my first. Similarly I can find T2, so this equation is alpha V square is equals to nRT, and at temperature T2 volume is eta times V naught is equals to nRT2. So from here I can find T2. So T2 is alpha eta square V naught square, and this divided by nR. So this is nR. So this is the temperature 2. Are you getting? Now internal energy change is very easy to find. So du n Cv dt, T2 minus T1. T2 is alpha eta square V naught square by nR, minus T1 is alpha V naught square by nR. So n goes out, throughout we have n. And Cv, if you remember, this is written as R by gamma minus 1. So R by gamma minus 1 into, and R also goes out, so let us take R common. So we will have alpha eta square minus 1 alpha, let us take eta square alpha V naught square if I take common. So this is V naught square. I can take alpha also common, so R goes. So we will have alpha, if I take common, alpha V naught square by gamma minus 1. This is equals to eta square minus 1. Are you getting? So this is alpha. And if I take alpha common, you will have eta square minus 1. Are you getting or not? You see here, what we are doing, I have cancelled n, and then I have taken R common. So you will have on the top, if I take V naught square also common, I will have alpha eta square minus alpha. V naught square is common. So this is the change in internal energy. Let us do the second part. Second part of the question says B. I think all of you have copied this one. Not copied. Let us copy fast and then we'll go for the next problem. Second part says find out the work performed. So dW, I have to find dW. And dW is nothing but integral P dV. And P is given by alpha times V dV. Are you getting or not? Things are very easy now. Now I can write alpha times V. So dW I basically integrate. So alpha is a constant. I can take outside. And V to dV. And initial volume is V naught. Final volume is eta times V naught. So this is V square by 2. So alpha V square by 2 V naught to eta times V naught. So this will be alpha. So alpha by 2, let us take 2 common. So eta square V naught square minus V naught square. So the work performed will be, if I take V naught square common, so alpha V naught square by 2 eta square minus 1. So this is again easy one. Now the third part says find the heat capacity, find the molar heat capacity for the process. So C part, molar heat capacity I want to find. Molar heat capacity for this process, that is C, and we have defined C is nothing but dQ by dt, and dQ can be written as using first law of thermodynamics. dQ is equals to du plus dW divided by dt, and du is nothing but ncv dt plus dW is nothing but one can write P dV divided by dt. So this is basically this is for 1 mole. This C is defined n dt. So I have to divide by n also. So n is here. So I will have Cv plus work done P dV divided by n dt. And in the first part we have already calculated the work done. So P dV I have already calculated in the second part. So I can write Cv plus P dV is what? Alpha V naught square by 2 eta square minus 1. This is the work performed. Basically I need to have P dV. I have to find P dV in terms of dt. And that one I can cancel dt. So let us leave as it is. So P dV divided by n dt. Now we have equation P is equals to alpha V. If I differentiate this equation, or let us say if I apply this in PV is equals to nRT, I want P dV in terms of, so if I plug the value of P, so this becomes alpha V square is equals to nRT. Now if I differentiate this equation, so this becomes 2 alpha V dV, this is equals to nR dt. Are you getting or not? Why I am doing this? Because I want dV to convert into dt so that I can cancel dV as dt. Now alpha V is nothing but P. Are you getting? So I need P dV. So alpha V is nothing but P. So 2 into P into dV is equals to nR dt. So P dV is nothing but nR dt divided by 2. Are you getting? So now I can plug the value of P dV here in the first equation. So let us say call equation 1. I can plug the value of P dV in equation 1. Why I am doing this? Because I want to cancel dt. Upper I have P dV, lower I have dt. So I want to cancel dt, and that's why I am doing all this calculation. So I will have now, I think all of you have copied this one. Let us copy this one and then I can go fast. Okay, so let us plug the value of nR dt by 2. So this line I can write from 1, that is P dV, that is Cv plus P dV is nR dt divided by 2 into dt into n also. So n goes out, dt also goes out, so I will have Cv plus R by 2. So this is my heat capacity C, Cv plus R by 2. Are you getting? If you want, you can also express in terms of gamma. CV is because R by gamma minus 1. R by gamma minus 1 plus R by 2. So you can express in terms of, if you take R common, and you will have 2 into gamma minus 1, and here you will have 2 plus gamma minus 1. So you will have R by 2, and up you will have gamma plus 1, and the bottom you will have gamma minus 1. Are you getting? So this is so simple. I think all of you are able to understand this one. So this is the C. So this is the general procedure to find C for any process. In this question, one important point we have: if you want to find molar heat capacity for any process, you do the same steps. What will be the steps? You write C is equals to dqi and dt, and then you write dq is equals to du dw, come up to this stage, and then you have to express this term in terms of dt. So I have to express PdV in terms of dt, and that's why I can cancel dt, and that is the only thing. So from given equation and ideal gas equation, you find PdV in terms of dt. You have to do this calculation some way so that you find dV in terms of dt. And once you know dV in terms of dt, PdV in terms of dt, you know the heat capacity. So this is a fairly easy problem. We will discuss the next problem. I think all of you have copied this one. Let us discuss the next problem.